我们开始上课好了。Before we move on, let me briefly remind you what we have done on Tuesday. We spent a lot of effort in deriving the equation about the gain, the saturated gain inside the laser cavity. So this is the result. G is the field gain coefficient. Can totally determined by this formula, where all you need to know is as I mentioned before, formula is not the most critical part. You do better, use some figures to impress the conclusion. So there are two cases. First, we consider the small signal gain, which is the gain when there is no lasing. If there is no lasing, your intracavity intensity is 0, or your stimulated emission rate is 0. Under these conditions, the formula can be simplified to this one, okay? Or can be illustrated by this blue curve. When there is no pump, you have no gain, for sure. Whenever there is any pump, you have non-zero gain. You have positive gain coefficient, which is the signature of four-level systems, as I emphasized before. And if you gradually increase the pump rate, you can get larger and larger gain coefficient, a small signal gain coefficient. But no matter how hard you pump the gain medium, the small signal gain coefficient is always limited by upper bound, which is Gmax. Okay? And as we have known, Gmax is determined by the material. The best you can get is pumping all the electrons to the excited states. That's it. Okay? The other case is saturated gain, which means the gain when there is intracavity light intensity. And by way of some mathematics, we derive this result. Your saturated gain coefficient is small signal gain coefficient over 1 plus a normalized number, which is the intracavity light intensity over a parameter saturation intensity I set, which is defined here. So the meaning of saturation intensity can be understood by this formula itself, which is when your light intensity happens to be the saturation intensity, your gain coefficient will be reduced by a factor of 2. Okay? G equals half of G0, half of the small signal gain. So you can imagine your light intensity probably cannot be much larger than the saturation intensity, because if you have a larger I, your gain will be quickly reduced. Okay? Then you do not have sufficient gain to support even stronger light intensity. So this is a good indication about the intensity you can have. Okay? Or quantitatively, you can arrive at this formula. In steady state, your light intensity inside the cavity is a factor, amplification factor of saturation intensity. And this factor is determined by the small signal gain over cavity loss coefficient minus constant 1. Okay? So this formula is interesting because whenever your small signal gain coefficient, the G0, is smaller than the cavity loss, you will have a number less than 1, right? Then minus 1 will give you a negative number, which is impossible because light intensity must be positive. So you can see there is a threshold that you have to pass through. G0 at least has to be the same or even larger than the cavity loss. Otherwise, there is no lasing. You cannot have steady state light intensity by just looking at this formula. And if you have stronger pump, you have stronger small signal gain, then this factor can be larger. So in steady state, you have higher intensity. Okay? And as I mentioned, saturation intensity is a good indication about the light intensity you can have in steady state. You can hardly imagine this is a big number, right? Good. But the central issue is, what is the steady state intensity given we know all the parameters, system parameters? There are two ways we can arrive at this purpose. Method 1 is by graphical solution. Okay? So the way is quite easy. First, you have to plot a series of gain versus pump curves at different light intensities. Remember that to this point, we have no idea about what is the steady state light intensity, right? There are many possibilities. But you just plot all the possibilities. Like when there is no light, no lasing, your gain curve is the blue one, which you have seen before, right? The small signal gain curve. When you have light intensity, like I equals I0, you got the red curve, which is the saturated gain curve, lower than the blue one, right? Because now you have light in steady state. The gain is smaller. So the red curve is shorter or lower than the blue one, the small signal gain curve. If your light intensity is even stronger, like 10 times of I0, you got the green curve, which is even lower. Okay? So imagine that you can plot essentially infinitely many curves on this figure. Each one corresponds to some specific steady state light intensity. Okay? Next, you can specify the pump rate, W equals W0, and the cavity loss, LC. These two parameters have to be given, right? To design a laser, you need to know the pump rate. You need to know the cavity loss, okay? If you know these two key numbers, you can locate a single point on this plot. The horizontal axis is determined by the given pump rate. If you know pump rate is W0, you can know the corresponding normalized pump rate, say here. If you know the cavity loss, LC, you know in steady state, the gain has to be equal to the loss. So you can determine the vertical coordinate. Okay? Vertical coordinate is about normalized gain. just substitute G equals LC. You can know the vertical coordinate. Then you can locate a single point, say, represented by this red cross. Okay? Then there is only one curve that can pass through this red cross. Okay? Say the black dashed curve happens to pass through this specified point. And the corresponding light intensity, say I equals Ix, is the solution. Okay? So do you know what I mean? The graphical solution. 2 steps. Step 1, plot a series of gain curves. Step 2, locate your position on the plot by the 2 parameters, the given pump rate and the given cavity loss. Then only one of the curves, gain curves, happens to pass through this point. And the corresponding light intensity is the solution. Ix is the steady state intensity under this condition. Okay? This method is illustrative, very easy to be understood, but another method is also helpful, the algebraic solution. You just directly solve the nonlinear equation, G equals LC, the same. Gain equals to loss in steady state. But gain as a function of pump is a nonlinear function of W, so this is a nonlinear equation. Say you can approximate the solution like this, or substituting the formula about G0, you can reach this result. The light intensity is a function of W, the pump rate. It's also a function of the cavity loss parameter, LC. But it's not a very simple formula. It's a nonlinear equation of W, right? You can see W here and here. So this is not a simple proportional relation. But it's the algebraic solution about steady state light intensity. Again, we can use a figure to help you what is the meaning you can get from this formula. Here I show you 3 examples. The blue curve represents the light intensity versus the pump rate when your cavity loss is smaller, say it's only 10% of Gmax. Okay? About 10% relative to the upper bound of the small signal gain. Then you got this blue curve. Okay? So roughly speaking, you see 2 characteristics. First, when the pump rate is smaller than this number, what do you have? According to this formula, you got a negative number, which is impossible. So you just set the output equal to 0. No lasing. Okay? But if the pump rate is greater than the threshold, what do you have? Your light intensity increases with the pump, which is reasonable. And even interestingly, the relation is roughly linear. Okay? And the same thing happens to other 2 cases. When your cavity loss is larger and larger, all these curves share the common features. Each of them has the pump threshold, below which no lasing, I equals 0. Above which light is roughly proportional to the pump. There is a linear relation. Okay? All of them share the common features. But what is the difference between them? You can easily conclude by this simple figure, right? If the cavity loss is bigger, what are the disadvantages? you will suffer. There are two things. Right. First one, you need a higher pumps ratio. If your pump is not big enough, you got nothing. You have larger cavity loss, this ratio is larger, which is worse, right? What's the second price you have to pay? Right, you can see the slopes are different, right? After lasing, there is roughly linear relation between lasing intensity and the pump rate. And the slopes are very important, right? If you have bigger cavity loss, you have smaller slope, which is worse. That means you have to provide more pump power to get smaller output power. The conversion efficiency is worse. From pump to lasing intensity, the conversion efficiency is worse, right? Very good. So these are roughly summarized in this slide. Okay. Light intensity is positive only when your pump rate is greater than the pumps ratio. Here I use a symbol W sub TH to represent pumps ratio. And by the formula in the previous slide, you can easily derive the pumps ratio is governed by this formula. Okay, you can just prove by yourself. Second, if the pump rate is pretty strong, which means W times tau G has to be much larger than 1, then the light intensity is nearly proportional to the pump rate. You have this relation. And the number within the bracket is simply a constant, independent of W. W is here. So I is roughly proportional to W. And the proportion coefficient, which is the total number inside the bracket, is denoted by eta, which is the slope efficiency of this laser. And this is the slope efficiency formula. Okay? Intuitively, you prefer a smaller pumps ratio and a bigger slope efficiency, right? Now you know how to manipulate the parameters to reach these goals, right? And in any case, both pumps ratio and the slope efficiency will degrade with the cavity loss. So cavity loss is the bad thing. If you have a bigger cavity loss, anyway, the laser behaves worse. Bigger pumps ratio, smaller slope efficiency. Okay. Any question? Before we conclude the review about CW lasers, there is one thing I have to emphasize. So far, we only analyzed the intracavity light intensity. What is intracavity? Inside the cavity. But the light intensity you can actually access is not intracavity light intensity, but the output intensity, right? 你能用到的光只有耦合出去的才行。目前我只分析的腔内的光，不是真的耦合出去的光。And if you consider the output coupling ratio, things could be pretty surprising. Okay? So here we assume the cavity loss coefficient LC is the summation of two terms, Li and Le. Li related to the internal cavity loss. Okay? For example, your GaN medium has natural refraction. Some light will be lost, right? That's internal cavity loss. Okay? And this number, internal cavity loss, denoted by delta sub I, is related to the loss coefficient Li by this relation. So if you have a very big loss coefficient Li, this term is close to 0, right? Then your internal cavity loss, delta I, is close to 100%, high loss. Okay? So the bigger the Li, the larger the internal cavity loss. Okay? But secondly, we have output coupling ratio, eta sub E, which is related to the loss coefficient L sub E by this formula. Very similar to the previous one. So if you have bigger LE, this number is close to 0 and the eta is close to 1. That means 100% output coupling. The partial reflector of the cavity has a large transmission. Okay? So actually we have two parameters in this case. And what is the output intensity that you can access? I out is the intracavity light intensity I, which we have analyzed before, times the output coupling ratio eta E, right? Under this model. So you can imagine if output coupling ratio is bigger, a larger percentage of the power inside the cavity can be coupled out for your applications. Okay? But this is both good and evil. It's analyzed like this. You have a larger output coupling ratio, eta sub E. You have a higher percentage of power which can be coupled out. This is good for your application, but you will also suffer from more cavity loss, right? Because output coupling is also part of the cavity loss, as shown here. Coupling loss coefficient LC is Li plus Le. If you have a larger E, your cavity loss is bigger. And according to our previous analysis, a bigger LC, a bigger cavity loss, will give you worse performance. You have larger pump threshold, you have lower slope efficiency. So you can figure out there are two counteracting forces in this mechanism. Increasing the output coupling ratio, you got more output power, but meanwhile, your laser intracavity intensity should be reduced. So if you have two counteracting forces, what do you expect? There must be some optimal number, right? 你一定会出现最佳化或者优化的这个参数出现。增加一项，然后就出现 trade-off， 那你就会有最佳点出现。So this figure illustrates what I have mentioned. Say we have, let's take a look at this lowest blue curve. Okay, this curve is obtained when we assume there is a 5 millimeter long YAG crystal for your lasing. And the pump rate is pretty high. W times tau G, the normalized pump rate is 20, which is a large number. And under this condition, I plot the output light intensity, vertical axis, versus the output coupling ratio, eta E. Okay? So you got this blue curve. That means when you increase, gradually increase your coupling ratio from 0, which is no coupling, all the way to maybe 20-something%, your output light intensity starts from 0 to the peak, then decrease again. the optimal output coupling ratio is somewhere here, maybe about 7.5%. If you have a smaller output coupling ratio or even larger one, you always get lower output intensity. Okay, so this is the optimal position, optimal output coupling ratio. But it's only valid when your internal cavity loss, delta I, is 10%. If you reduce the internal cavity loss, delta I, say from 10% reduced to 5%, you got a different curve, the orange one. Okay? This time, your optimal intensity is bigger because you have smaller internal cavity loss. It's good. So you got brighter output intensity, but meanwhile, the optimal output coupling ratio is slightly reduced. It's different. So each curve in this figure shows the relation obtained at different internal cavity loss. Okay? So the tendency is quite evident. If you have smaller and smaller internal cavity loss, you got the curve taller and taller, right? Which means you have brighter and brighter output light intensity, which is good. Simultaneously, the optimal output coupling ratio is roughly follows this red dotted curve, smaller and smaller. So that means your partial refractor has to be less and less transmissive. The refractivity has to be larger and larger if you have a smaller intracavity loss, internal cavity loss. Okay? So this is something more close to the real world. You need to consider not just the light inside the cavity, but also the output coupling ratio. Okay. Any question?